This is the first 8.3 video where we're going to look at how to create a confidence interval for a population mean. So we're going to use the same basic formula for a confidence interval. We use our point estimate plus or minus the margin of error. One of the differences now is our point estimate is going to be x bar because we're trying to estimate a population mean mu. But the basic formula still stays the same, and I'll show you a couple of minor changes. You might remember the confidence interval or how to create a confidence interval for a population proportion, where the only necessary things are your point estimate, p hat, the critical value, and the sample size, and that will allow you to create your confidence interval to try and capture a population proportion. Here is the confidence or the formula for a confidence interval when you're trying to estimate a population mean. X bar is your point estimate, plus or minus, critical value is Z. And then this, you might remember, is the standard deviation of the sampling distribution of X bar. And so the first thing we have to consider is if we're trying to capture an unknown population mean, then it's highly unlikely that we know the population standard deviation. Because in order to calculate the standard deviation of a population, you have to subtract all the observations distances from the mean. So it's very, very, very unlikely that we know the population mean. So instead of using the population mean, then what we try and do is we substitute our sample mean to try and estimate the population standard deviation sigma. And I've got a picture here at the bottom I'll explain in a second, but when we substitute the sample standard deviation for a population standard deviation, the distribution starts to change and we have to actually use a t distribution rather than a z distribution. So now I'm going to talk about what is this t distribution and how is it different from our usual z distribution. So when we use the sample standard deviation as an estimate for sigma, it doesn't work out exactly the same. So here's an example of this line right here represents, you remember doing the simulator for how a confidence interval works. These black dots right here represent a sample mean, and then we've built a confidence interval to try and capture this population parameter. So the green intervals represent intervals that captured the true population mean, and these red intervals are the ones that were unsuccessful. They didn't actually capture it. So you can see we are estimating with the confidence interval with S, the sample standard deviation. So here are 1,000 intervals, and we're using a 99% confidence level with Z as our critical value, but only 92.5% of the intervals actually captured mu. Our success rate, we said, was supposed to be 99%, but in this simulation, it was only 92.5%, and we did 1,000, so we did a lot of simulations. So the issue is if we use a Z critical value, our success rate isn't actually what it's claiming to be. And that's because when we substitute the standard deviation of the sample in for the population, then we have more error and there's more variation in the distribution. So that's why instead of using a Z distribution, we've determined that through trial and error that we should be using what's called a T distribution. And the T distribution is really similar to the Z distribution, but it has more area in the tails. It's more spread out. I'll show you a picture in a second. So to achieve a 99% capture rate, we need to multiply by a larger critical value, and the T distribution will give us a larger critical value. So here's a picture of what the T distribution is. And the T distribution is all based on the degrees of freedom. Degrees of freedom is real simple. It's your sample size minus 1. So like all distributions is based on the size sample you're taking. And the formula for degrees of freedom is just the sample size minus 1. So there's an infinite amount of T distributions because they all depend on the sample size. You can take an infinite amount of different sample sizes. As your sample size gets larger and larger, the T distribution becomes more and more like the Z distribution. And the Z distribution is the standard normal curve with the mean of 0 and standard deviation of 1. So you can see a picture here, just giving you an example of two T distributions that have specific degrees of freedom. So the red dotted line is 2 degrees of freedom, and you can see that the area here underneath this tail is much larger than the standard normal curve or the Z distribution, which is the purple here. But as we increase the sample size, so this, if it has 2 degrees of freedom, it means the sample size is 3. And this is degrees of freedom of 9, which means the sample size was 10. And you can see the area in the tails, it starts to get more and more like the Z distribution. And so you should remember standard normal is just the Z distribution. So really all you need to know is if we don't know the population mean sigma, and we're using sample standard deviation to estimate it, then we're going to have to use a T critical value rather than a Z critical value. So our confidence interval, the formula for our interval, is actually going to change. It's very rare that we're going to use this confidence interval right here. And I'll talk more about what the actual formula is in a moment. Before we can actually calculate a confidence interval, we're going to have to look at our first objective of how do I calculate what a T critical value is. So first objective, determine the critical value for calculating a C% confidence interval for a population mean using a table or technology. So you're going to see here in a second table B, and table B is just like table A, but table A gives the area from the Z distribution. Table B gives the areas from the T distribution. And I'm going to show you how to use technology because that's the best way to do it. So what critical value T from table B should be used in constructing a confidence interval for the population mean in each of the following settings? Confirm your answer using technology. So I'm just going to use technology. A 95% confidence interval based on an SRS of size 12. The process for finding a T critical value is the same as it was for finding a Z critical value. We're looking for the central 95%, which means this area here is going to be 2.5%. This area here is going to be 2.5%. So we're really looking for the 2.5th percentile. That will give us the negative critical value, or the 97.5th percentile. And it's the 97.5th percentile because this positive critical value is above 97% of all other T values. And again, one will be negative, one will be positive. So in our calculator, we're going to do actually inverse T instead of inverse norm. When we do inverse norm when we're doing a Z distribution, but it's called inverse T when we do a T distribution. I'll go to my distributions, second vars, and I will go to inverse T and hit enter. And I'll need two things. My area, 0.025, because it was the 2.5th percentile. My degrees of freedom is 11 because my sample size was 12, so subtract 1. Then I can paste, and I get a negative critical value of 2.0 or 2.201 or 009. The two inputs reminder are the area, degrees of freedom. It gave me the negative critical value. That's this one here. When you write your answer, you can always just write it as a positive value because in the interval, remember, you're going to use the negative and the positive. So my critical value is 2.201. Now let's see, I'll pull up the table B and show you quickly how you could do that if you don't have inverse T for some reason. Here's the table of critical values for the T distribution. So what we're doing is we're looking at the bottom here. This will give us our confidence level. So we wanted 95% confidence. So you're going to follow it up and match it with your degrees of freedom, which we had 11 degrees of freedom. And so if we follow that over to our 95%, that's telling me my critical value is going to be 2.201, which we saw previously. So if we wanted a 90% confidence interval, we just look up here for the degrees of freedom that we need. We'll do one more critical value for a T distribution, a 90% confidence interval from a random sample of 48 observations. Now I'm looking for the 5th percentile of the T distribution or the 95th percentile of the T distribution. This time I'll do the positive critical value from the calculator. Second var to distribution inverse T, looking for the 95th percentile. Degrees of freedom is 47. And we get a critical value of 1.6779. With our calculator, we get the 1.6779 critical value. But let's take a look at the table again, and I'll show you an issue that you might run into if you don't have a calculator. On table B, again, we need the confidence level, which they told us 90% confidence interval. And then our degrees of freedom was 47. So as you'll see, our degrees of freedom counts by ones, and then when it gets to here, it starts counting by tens. So we don't have degrees of freedom exactly equal to 47. So we have to pick the most conservative estimate, which as our sample size increases, the variation decreases. So the spread decreases. Well, we don't have a sample size of 51. We have a sample size of 48. So we have to pick the most conservative estimate, which would be 40 in this case, because this distribution has more spread. And so we're going to follow from 40 over, and our critical value, according to table B, would be 1.684 rather than the 1.6779 we saw in the calculator. The calculator is more the calculator is more accurate because it actually gives us the appropriate degrees of freedom. Here, we have to be conservative and approach with the degrees of freedom that is closest based on what the table can tell us. So that's why this value is a little bit larger, because it's more conservative than the true T critical value.